Every single time you click a link or type in a web address, you're tapping into one of the internet's oldest, most critical systems, and you probably don't even think about it. Well, today, we're going to pull back that curtain. We're diving deep into the domain name system, or DNS, to really get our heads around the incredible architecture that makes the web, well, work. Okay, so really think about this for a second. You type a simple name into your browser, and bam, in milliseconds, you're connected. But how? How on earth does your computer navigate this absolutely massive, chaotic network of billions of servers to find the one right place? That's the huge engineering problem that DNS was designed to solve from day one. So, at its heart, you can think of DNS as the internet's phone book. It's a classic analogy for a reason. But here's the thing. We're not talking about a phone book for a small town. We're talking about mapping billions of websites to their IP addresses. That unique number for every single device on the network. The sheer scale of it means a simple list is just completely out of the question. You need something way, way more sophisticated. So let's really focus on that core function first. The entire system, its whole reason for being is to translate something that's easy for us humans, like educative.io, into something a machine can actually use. That machine-readable IP address, like 104.18.2.119. And this is the really crucial point, right? We humans, we remember names. But computers, the actual network infrastructure, all those routers and switches, they only speak in numbers. So DNS is that essential translator. It's the bridge between how our brains work and how the network really works. Okay, so how in the world do you build a phone book for billions of entries that has to respond almost instantly? You can't just stick it all on one giant server, right? It would just collapse. Instead, DNS is engineered as this massively distributed hierarchical system. The best way to picture it is like an upside-down tree. And this hierarchy has 4 key players. It all kicks off with the DNS resolver. Think of it as your local guide for this journey. First, the resolver talks to the root servers, which are at the very top of that tree. They don't have the final answer, but they know who to ask next. They'll point the resolver to the right top-level domain server, or TLD server. That's the one that handles all the .coms or .ios. And then that TLD server points to the final stop, the authoritative name server. That's the server that actually holds the IP address you're looking for. This whole distributed setup is the absolute key to why DNS is so scalable and so resilient. Now, the information that gets passed back and forth between all these servers comes in a specific format. They're called resource records. You can just think of them as the actual lines written in that giant phone book. The most common one you'll hear about is the A record. That's a simple direct mapping of a name to an IP address. But there are other types too, like NS or CNAME records, which handle more complex stuff, like figuring out which server is the official one for a domain. Okay, so we've got the pieces of the puzzle. We know the servers, we know about the records. So now let's follow the journey of a single DNS query, from the very beginning to the very end. This is where you really get to see that amazing hierarchy in action. And this process is just brilliant. It's what we call an iterative process, kind of like a game of ping pong. Your local DNS resolver does all the heavy lifting. It goes to a root server and asks, hey, where's educative.io? The root server says, I don't know, but go ask the IOTLD server. So the resolver does. It asks the TLD server, which replies, nope, not me, but you should ask its authoritative server. Finally, the resolver asks that authoritative server, and that's the one that gives up the final IP address. What's so crucial here is that no single server knows the whole map. Each one just knows who to point to next. And it's really important to understand that this iterative process, where your resolver does all the chasing, is the preferred way to do things. There is an alternative called a recursive query, where you basically ask one server to go do all that work for you. But the iterative model is just so much better for the health of the internet. It spreads the workload out, which stops those super important root and TLD servers from getting totally overwhelmed and becoming bottlenecks. All right, so we've got the mechanics down. Now let's switch gears and talk about what makes this whole system so incredibly fast, because it all comes down to some really smart engineering decisions and some very deliberate trade-offs. One of the biggest performance wins for DNS was the choice of transport protocol. See, DNS mostly uses something called UDP. It is blazing fast because it doesn't waste time setting up a formal connection before it sends data. The analogy I love is it's like sending a postcard instead of having to make a full phone call. Now, you sacrifice the guaranteed delivery you get with the slower protocol TCP, but in return, you get raw speed. And for a quick lookup, that's exactly the trade-off you want to make. The other absolute hero when it comes to performance is caching. I mean, think about it. You don't want to go through that whole lookup dance every single time you visit a site, right? So DNS answers get cached everywhere. Seriously, in your browser, in your operating system, at your internet service provider. It's this caching that dramatically cuts down on delays and takes a huge load off the global DNS system. But that raises a good question. How do you stop that cached information from getting stale and out of date? Well, every single DNS record comes with an expiration date. It's called the time to live, or TTL. It's basically a little timer that tells the cache, hey, you can use this answer for this long. But after that, you've got to throw it out and come ask me for a fresh one. Okay, so this whole system of caching and expiration dates, it all leads us to one of the most important design philosophies of the entire internet. It goes way beyond just DNS. It's this idea called eventual consistency. And this quote right here, it just nails it. The DNS system is read from billions, maybe trillions of times more often than it's ever written to. So the engineers optimize the whole thing for lightning-fast reads, even if that meant that updates, well, they might take a little while to ripple through the entire system. And that brings us to this number, which can be pretty staggering when you first hear it. Because of all those layers of caching spread across the entire globe, when someone updates an IP address, it can take up to 3 days for that change to reach every single user on the internet. That means, for a while, different people in different places might actually be sent to different servers for the same website. And this is the big takeaway, the most important thing to understand. That delay, it's not a bug. It's a feature. It is a deliberate design choice. This trade-off, giving up immediate, perfect consistency, is exactly what makes DNS so incredibly resilient, so highly available, and so fast on a global scale. Honestly, without that trade-off, the internet as we know it just wouldn't work. So we'll leave you with this question to chew on. This fundamental compromise, baked right into the DNA of the internet, is all about prioritizing a fast and reliable experience over having perfectly up-to-the-second data. It has shaped everything about how we build for and experience the web today. So, is this trade-off between speed and consistency the single most important design decision in the history of the internet? It's definitely up there.